The first problem. Show that the following inference is not correct. Suppose every node has a neighbor which is a neighbor of every other node. Then every node is a neighbor of every other node. If we formulate the assumption in predicate logic, it has a form: for all x there exists y, left parenthesis x e y, and for all z, left parenthesis, negation y equals z implies y e z, right parenthesis, right parenthesis. And the conclusion, if written in predicate logic, is for all y, for all z, left parenthesis, negation y equals z implies y e z, right parenthesis. So the problem is to show that there is no natural deduction of for all y, for all z, left parenthesis, negation y equals z implies y e z, right parenthesis, from the sentence for all x there exists y, left parenthesis, x e y, and for all z, negation y equals z implies y e z, right parenthesis, right parenthesis. We use the soundness theorem. Let G be the graph on the right. This is a graph of 4 vertices and 5 edges. We can observe that for every vertex in this graph there is another vertex which has the property that it has an edge to the first, and moreover it has an edge to every other vertex. This is because we can always pick one who is an extreme left vertex or an extreme right vertex. They have the property that they are neighbors of every other vertex. But on the other hand, it's not true that for every y and z in this graph, if they are different, then there's an edge, because the top vertex has no edge to the bottom vertex. So, by the soundness theorem, there can be no natural deduction of the kind asked. Here's a picture of all valid 2-quantifier implications, starting from for all x, for all y, r0, xy, going through all kinds of intermediate stages to the weakest, there exists x, there exists y, r0, xy. Each green arrow can actually be proved by given a natural deduction, usually very short and simple one. And in fact, no arrows can be reversed, and no arrows can be added except the ones which follow transitively from these arrows. To show that no arrows can be reversed in each case, for each of the 13 arrows, one can construct a model which satisfies the hypothesis of the arrow, but not the conclusion. And in each case, it is a very simple model. But these simple deductions and simple models show that this picture gives a complete picture of the correct implications between 2-quantifier formulas of this very simple form, just 2 quantifiers and then an atomic formula. Let us finally consider equivalence relations. Equivalence relations are models which have a binary predicate x equivalent to y, denoted by these 3 lines, a little bit like x identical with y. The axioms of equivalence relation are symmetry axiom: for all x, for all y, x equivalent to y implies y equivalent to x. Reflexivity axiom: for all x, x equivalent to x. And transitivity axiom: for all x, for all y, for all z, left parenthesis, x equivalent to y and y equivalent to z, right parenthesis, implies x equivalent to z, right parenthesis. In the next lecture, we will consider other similar axiom systems or sets of axioms. So now from these axioms, which means just from these sentences one can deduce the following: for all x, for all y, for all z, left parenthesis, x equivalent to y and z equivalent to y, right parenthesis, implies x equivalent to z, right parenthesis. And here is the derivation, the natural reduction. It looks rather bad because it is so big, but it is big only because there are all those universal quantifier elimination rule applications and then the universal quantifier reduction rule applications. But apart from that, it is a very simple derivation. Now, if I proposed that one could prove from the three axioms of equivalence relation, for example, that for all x and for all y, x is equivalent to y, it would be very easy to show that I cannot be right about that, because one just constructs a model with an equivalence relation in which it is not true that all two elements are equivalent.